Hello students, let us do a quick review to in-class exercise 1 for topic 17 carbonyl compounds. For the first question, we have lactic acid, otherwise known as 2-hydroxypropanoic acid. You are given the formula. Based on the formula, you know that there is a chiral carbon right in the middle over here. Okay, then it's present in milk. You were also told that it can be made in the laboratory from ethanol by the following reaction. Okay, so you have step 1, and then you realize that in step 1, the CN is being added, probably across the CO double bond. Just to let everyone know that whenever a formula is written as CH3CHO, CHO represent aldehyde functional groups. Yeah, so please do not write aldehyde as CH3COH. Okay, so this is incorrect. If you want to write an aldehyde out, it should be written as CH3CHO. Okay, so clearly step 1 is a nucleophilic addition step, and then step 2, you realize that the C triple bond N is gone, and then you get a carboxylic acid. Yeah, so step 2 should be acidic hydrolysis, something which you are very familiar with from the topic halogen derivatives onwards. Okay, so for question A, part 1, you are supposed to name the reagents and conditions used and type reaction for step 1. So clearly this is nucleophilic addition. So if it's nucleophilic addition, then we just need to look at our notes. What we need is HCN, okay, with trace amount of KCN as the catalyst. Okay, so the trace amount of KCN provides the cyanide nucleophile, which allows the slow step of the nucleophilic addition to take place before the alkoxide being formed is being used to deprotonate HCN and produce more CN minus. Okay, so the condition will be cold. Okay, so some of you might recognize from the old curriculum that in the old curriculum we need the students to write 5 to 10 degrees Celsius, but this is not required for the current curriculum because we don't need you to remember the exact condition. Okay, another reason why we don't need you to remember the exact condition is because probably for every aldehydes, ketones, the condition will differ slightly. And if you look at your notes carefully, the reason why we need to perform the reaction under cold condition is to ensure that your HCN does not vaporize. Okay, yeah. So A2 is a very straightforward mechanism question. You are required to describe the mechanism for this reaction, and then in your answer you should draw all curly arrows, lone pairs, charges, okay, so etc. Okay, so as per all question, if you remember from the very beginning when we first discussed free radical substitution for alkanes, you need to write down the name of the mechanism. Okay, so the name of the mechanism is nucleophilic addition. Okay, you need to write it out clearly. Okay, so for nucleophilic addition, the first steps involve the nucleophilic attack by the cyanide nucleophile. So this is the slow step. And then there is a need for you to write down the charge separation, delta plus, delta minus. Okay, and then the cyanide nucleophile. Remember that for cyanides, the carbon is the one bearing the negative charge. Okay, and the lone pairs of electrons, which is the nucleophilic source. Okay, so attack the carbonyl carbon, and then the CO pi bond break towards the oxygen. And then in the process, you form this particular alkoxide intermediate. Okay, so O minus. Okay, and then remember to put down your lone pairs of electrons on your O minus, because later on in your fast step, okay, then you can clearly show the deprotonation of HCN. Okay, so the deprotonation of HCN begins from the lone pairs of electrons on the alkoxide attacking the electron deficient hydrogen. Okay, so this is the protonic hydrogen, and then the HC bond will break heterolytically where the carbon will gain the lone pairs and the negative charge. Okay, and then yeah, so this is the nucleophilic addition step. So you have a CNH and then OH plus CN minus. Okay, so it is of vital importance for you to show the regeneration of the cyanide catalyst. Yeah, I think that's about it. Okay, so make sure you understand that the phrasing to the question for mechanism for H2 tends to be always something along the line. You need to show all charges, lone pairs, and the movement of electrons using curly arrows. Yeah. Okay, then The next part, lactic acid is present in milk, rotates plain polarized light. Lactic acid produced in the laboratory by the reaction above does not rotate plain polarized light. So what feature of lactic acid present in milk causes the rotation of the plane of polarized light? Okay, so that the structure you probably will be aware of is that, I think number one, the lactic acid contains a chiral carbon. So that means it has an asymmetrical carbon bonded to 4 different groups. Okay, then why is it that in milk it can rotate plain polarized light, but in the lab it can't? I mean, in a sense, the lactic acid produced in the lab by the above reaction, so by this particular nucleophilic addition, why is it that it can't rotate plain polarized light? Okay, so for the lactic acid present in milk, we can safely conclude that it contains only one enantiomer. So the lactic acid in milk, okay, contains only one enantiomer out of the 2, of course. Okay, yep. However, the one you produce in the lab using the above method, right, you will notice that in the slow steps, which is this particular step, I'm going to box it up. Okay, so I'm going to showcase to you below. So if we show the stereochemistry of the group, so we have a methyl group projecting in, a carbonyl carbon, and an H projecting out. Okay, so you notice that the carbonyl carbon, right, is trigonal planar about, okay, the carbonyl carbon. Okay, so in terms of geometry, so in that sense, right, your cyanide nucleophile can will then approach it from the top and bottom plane with near equal probability. So this is the top approach, and then this is the bottom approach. Okay, so then the CO pi bond will then break accordingly. Yeah, so because of this, in the process, right, racemic alkoxide intermediates, okay, will be produced, okay, because the geometry about the carbonyl carbon is trigonal planar. Okay, allowing the cyanide nucleophile to approach it from the top and bottom plane with near equal probability. Okay, yep. And after protonation, I'm going to get a racemic product mixture. Yeah, so because I get both the enantiomers, so the plane polarized light will be rotated in both directions, and then eventually it will cancel out. Okay, so therefore the product mixture you get at the end of the day from the synthesis in the above steps is not able to rotate plane polarized light despite having a chiral carbon. Alright, so I hope this is clear enough. Most of the things you probably need to know here are actually coming out directly from the lecture notes. So yeah, so this represents some of the basic concepts you need to be aware of when you are dealing with this topic. If you look at question 1, it's actually related to the chemistry of magnesium, and we know that most of the chemistry we are aware of is its ionic compounds, but magnesium forms a special group and also an important group of compounds known as Grignard reagents. Ever since this particular question came out in 2010 for A-levels, many JCs have said it in their school-based exams. So you might have seen it once in a while when you're doing some of these questions. Okay, after that they give you some history about the fact that it was developed by this French chemist known as Victor Grignard. Okay, and you warm it with a solution of bromoethane in dry non-polar solvents, and you will obtain a solution contains what we call ethyl magnesium bromides. Okay, so this ethyl magnesium bromides. Many Grignard reagents with different alkyl groups and aron groups have now been prepared and used widely in organic synthesis. Okay, if you are pursuing a career or a degree in chemistry, you would have prepared Grignard reagent in your year 2. Okay, some university even let the year 1 students do Grignard reagents. So it has been so widespread, so popular, and so fundamental that any chemistry students will probably prepare Grignard reagents once in their lifetime, at least in the research lab. Okay, so you have typical examples of the use of a Grignard reagent in the 2-step reaction of ethyl magnesium bromide with propanones. In the process, you get a tertiary alcohol known as 2-methyl butane 2-ol. Yep, and then you notice from here that at first maybe you think that it's not something which is very familiar, but you realize that if I just color code propanones, just the CH3 group, which is over here, and then after that I'm going to color code the ethyl bromides, the ethyl group, right? You'll notice that it kind of like it's being nucleophilic added to the carbonyl carbon. Yeah. If you simply recall from what you have studied in the topic on nucleophilic addition, this actually looks very familiar. Yeah. And then if I'm going to color code further, you notice that the following steps, the MgBr is now being removed, and then eventually I'm going to get the hydroxy group out. In this case, I'm going to produce the tertiary alcohol. Yeah. So in our case here, the ethyl group behaves as a nucleophile. It might seem a bit surprising, but if I'm going to look at the structure, you'll notice that it will not be very surprising. Okay, so if I'm just going to sketch my ethyl group out in terms of the structures, it will look something like this, and then I have a MgBr. Okay, it's a sigma bond. There's no mistake here. And if you notice, it is sigma bond. The carbon is sigma bonded to magnesium, which is an element less electronegative than itself. So therefore, I expect the bond to be quite polar. Yeah. And usually carbon will take on a partial positive charge, but in this case, because it is bonded to an element less electronegative than itself, it will take on a partial negative charge. And that explains why it behaves as a nucleophile in nucleophilic addition. Okay, so now let us jump straight into part 1. What type of reaction takes place in step 1? I think we have already indirectly answered this particular question, because when we were drawing out the structure for ethyl magnesium bromide, we highlight that the carbon directly bonded to the magnesium takes on a permanent partial negative charge. So therefore it behaves as a nucleophile. So the first step is therefore nucleophilic addition. So I don't think it comes as a surprise to many of you. So there will be nucleophilic addition. Okay, then if we are going to move on to the next step, suggest the types of reaction that occurs in step 2. Yeah, so you notice that in step 2, right, before we decide what kind of reaction this is in step 2, I think we might want to discuss what might OMGBr looks like, or how will it look like. Okay, so you can have different perspective on how this looks like. It can be viewed as simply an oxygen sigma bonded to MgBr. So this is one perspective you can look at. Yeah, so if it's sigma bonded to MgBr, I think it should be quite obvious that the O will take on a partial negative charge, the Mg will be a partial positive charge. Yeah, and then in the course of the reaction, the OMG bond breaks, and then H is being added. So that's some form of protonation reaction. So you can view it as an acid-base reaction, or it can be called a protonation reaction. But acid-base might make a little bit more sense. Okay, or you can even call this a hydrolysis, because any of such reaction where the O something bond breaks and then it involves water. Because how do we know it involves water? Because we were not told what exactly is used in step 2. Are we told? Let us take a look. Yeah, we were not told what happened in step 2, but because the byproduct is MgOHBr, so it does make sense that probably water is being added. Yeah, so acid base works, and because water is being added, we can also view this as some form of hydrolysis reaction. Okay, so we can also look at step 2 as hydrolysis. Okay, or you can call it acid base neutralization. Okay, so both of this works. And then finally for part B, suggest the structural formula of the final organic products formed when I'm going to use this particular magnesium bromide. So this should be phenyl magnesium bromide, is reacted with ethanol in a similar two-step process. We are just supposed to draw the final organic product. So in this case, there are a few things we can do. This will be the so-called the aryl group being added. So the nucleophilic carbon is over here. So this is delta minus delta plus. Okay, so because we are adding it to ethanol, what we need to do is just to follow the whole thought process of what exactly went on above. Okay, so if it's ethanol, then I have a carbon here, bonded to a H, bonded to a CH3. Okay, then of course there will be a phenyl ring bonded to it, because the phenyl ring is the nucleophilic site, and then of course not to forget the alcohol being produced as well in the course of the reaction. Okay, then next we are going to look at part C. The Grignard reagents, this is propyl magnesium bromides, can be easily converted into a carboxylic acid by using carbon dioxide. Okay, so this is the nucleophilic sites. Okay, so we have a nucleophile over here, and then suggest a two-step sequence for this particular conversion and giving the structural formulae of the compounds involved. Okay, this might be a bit challenging, but we are looking at the production of carboxylic acids from carbon dioxide. So if you look at carbon dioxide, right, it can be viewed as a compound containing two carbonyl oxygens in the stricter sense. So with that, because there are two C-double-O, you expect a delta plus, delta minus, and then a delta plus over here. Oh, sorry, a delta minus over here. Yeah, so because we are looking at the ethyl group as like a nucleophile, so if I'm going to sketch out a mechanism, MgBr, so I expect a delta minus, delta plus. Yeah, so if it's going to be a mechanism, then it will be a nucleophile attack at the carbon bond, double bonded to the two oxygen, and then one of the pi bond break. Okay, so we are just following the same thought process as above. Okay, and where we are adding to the carbonyl carbon of the carbon dioxide in that sense. Okay, so with that, then what I'm going to get here is I'm just going to draw out the ethyl group, sorry, the propyl group. Okay, and then bonded to a C, double bond O, and then you expect an O minus, but remember earlier on, the O is bonded to MgBr, so I'm going to just write it out as OMgBr. I'm just following what happens above. And then of course the next step is likely to be a hydrolysis step, so I'm just going to draw out the carboxylic acids. Okay, OH. Okay, and then MgOHBr. Right,